we had a series of lectures on operating system, where we have started with what are the various types of operating systems and the functionality of the operating system. In that, we discussed about the modular approach in case of operating systems, whereby we have got one major module over there, which we say is the process management there. Now, in the process management only, we have got a number of processes which we wanted to execute, what are the resources required for the execution of the processes. Sometimes it happens maybe there are two processes who are waiting for the same resource which is being held by the other process. What does it lead to? It leads to a state whereby each one is waiting for the other to leave the resource. That sort of state we call as the deadlocks. So, maybe in today's lecture we are going to cover up most of the aspects of the processes deadlocks. Maybe deadlocks do occurs in our daily lives also. Now, in this deadlock lecture we will be covering up this, maybe what sort of models are there, what sort of deadlocks, how exactly we say deadlock has occurred. Now, how exactly we can prevent or we can detect the deadlocks, or we can recover from the deadlocks. Maybe we as far as our approach is concerned, we try to have an approach whereby all these three approaches we try to combine and get into a single approach there. Now, what is the deadlock problem? Now, this deadlock problem do occurs in our daily lives also. Let us say I am waiting for something which is being held by the other fellow. I am holding something which he needs and he is holding something which I need. So, how do we handle this sort of a state? Maybe in case of our day to day working, what we do is we try to compromise. So, same is true over here. In case of a deadlock problem, it can be set of block processes, each holding a resource and waiting to acquire a resource held by the another process in the set. Maybe we can think about a system. Let us say there is a system which has got two tape drives, and P1 and P2 both of them are holding one tape drive each. Now, let us say P1 needs another tape drive. Now, what will happen in that particular case? I do not have got a tape drive there. Now, I am waiting for P2 to leave the tape drive. Now, in that particular case what happens is, let us say this is what will happen, each one of the holding one tape drive and waiting for the other tape drive to be left by the other, or it happens in case of semaphores also. In case both the semaphores are initialized to 1. Now, as far as journal problems is concerned, let us say this is the situation, let us say this is a wider road which we have got and this is another wider road we have got. Now, there is let us say there is a small bridge here. Now, what happens in this particular case? Maybe in this particular scenario two vehicles can pass in both the directions, whereas the moment vehicles comes over here, let us say only one vehicle can pass. Let us say one vehicle comes from this direction, another comes from this direction. What will happen in this scenario? Maybe since only one vehicle can pass, so this is a state of the deadlock. Maybe now what is the resource in this particular case? My bridge, whatever bridge we are talking about, that is a resource which is there, and what I am trying to do is I am trying to hold say okay, this resource is there which is to be used by one of the vehicles. Now, this vehicle is waiting for him to go back and this vehicle is waiting for him to go back. Now, what is the state? No vehicle can pass through this particular thing. Now, in a day to day lives, what sort of solution we have got for this sort of states? Maybe both of them are waiting, this is waiting and this is waiting, both of them are waiting other to leave the resource there, or he is a gentleman, he goes back, then this vehicle can pass, because then what has happened, this particular vehicle has left the resource which he was holding, or both were adamant. Then what will happen in that particular state? They will keep on struggling, who will leave the resource which is being held by the other. So, this is what we say, these are some of the solutions which are there for the deadlocks. I may be too nice leaving the resource, or both of them are too hard not to leave the resource. So, that will lead you to some state of the deadlock. Now, how to resolve the deadlock? Only resolving part is if one of the car goes back. That is what we call as a preemptive resources and rollback. Okay, what we are doing is one process which was in the state of execution preempt all the resources and gives it to somebody else, and it rolls back to some state. Now, what is the rollback state in this particular case? Let us say this vehicle comes over here, because this will be its safe state. Maybe I have reached to a state which is safe for me. Maybe let us say in case number of cars are there, maybe I had to roll back number of cars in this particular case also. Now, maybe another thing which happens is, let us say this fellow goes back and this fellow passes. The moment his turn comes, there is another car which comes from this direction, he allows this car to also pass. Maybe while again his turn comes, there is another car which comes over there. This do happens in our day to day lives also. Now, what is happening to this particular car which has come to this place? All the time it is waiting for the resource to be free. So, that is what we call as the starvation. Maybe this particular process gets into a state which is we call as the starvation state. Okay, it is waiting for this resource which we call as a bridge to be free, so that he can just pass through this particular bridge over there. So, this is the problem which we call as the deadlock problem. Now, what is as I said initially, okay, one process holding the other resource. Now, in case of our computer processes, I may be holding tape, I may be holding a printer, I may be holding some other device which is a non-shareable one. Now, had it been shareable, perhaps both of them can use the simultaneously, but this particular thing is not shareable. I cannot preempt, I cannot share it with some of the other things also. Now, what sort of a system model is there? Okay, let us say this is the resource type, maybe R1, R2, Rm, they are all of the type resources, maybe it is a CPU cycle, memory space or the IO devices. These can be some of the resources types it can be. I can have a CPU, let us say one process holding the CPU, other process waiting for the CPU to be free, or one process holding a printer, other process waiting for the printer to be free. So, this is what we say each resource type Ri have got Wi instances. What does it mean? That is each, let us say I have got a printer. Now, maybe there are two printers on my system. So, in that case my Wi will have the value 2 and resources my printer only, let us say. Now, what can be the usual process of resource sharing, resource utilization by any process? It requests for a resource. What does it mean by request? Okay, it tells to the operating system, okay, I need a printer for utilizing over here. Then he uses, and then once its usage is over, it requests for the release of that particular resource here. So, this is the way in our daily life also we do it. We request for something, we use it and then we leave it. Now, what are the conditions for a deadlock to occur? That is what we call as a deadlock characterizations. One of them is a mutual exclusion. That is mutual exclusion, only one process at a time can use a resource. Let us say there is a resource, my resource is such that it is a non-shareable. Had it been shareable resource, maybe two processes can use the same resource at the same time. Let us say I have got a file, file is a editor file. Since nobody is going to write anything to the editor, so what will happen? Any number of people can use that sort of a resource. So, there will be no deadlock as far as my word will be concerned, as far as my any of the executable programs is concerned. Now, another then what can be the resource which can be there for the mutual exclusion? Maybe non-shareable resources. So, whatever resources which we have got, they are non-shareable. We say those are the resources which are non-shareable there. And another is hold and wait. Now, what should be done by this is, okay, let us say one process is holding one resource which is to be utilized by the other process. Maybe I can explain you on the board better. Let us say there is two processes. Let us say this is my process Let us say this is process P 1, this is P 2, and these are the resources which are there. Now, what is this doing? P 1 is holding this particular resource R 1 and P 2 is holding the resource R 2. Let us say R 1 and R 2 can be any type of a resource there. Now, this is what we say is hold state. Okay, P 1 is holding R 1, P 2 is holding R 2. That means, this particular resource has been requested by the process P 1, this resource has been requested by the process P 2. Now, what is the next they are doing? Now, P 1 is waiting for resource R 2 and P 2 is waiting for the resource R 1. So, this is what we say is a hold and a wait state. I am holding R 1 and waiting for R 2, and same way P 2 is holding R 2 and waiting for R 1. So, this is what we call say it is a hold and a wait state. Now, another is no preemption. The moment I hold this particular resource, I will not leave this resource till the time I have utilized this resource for my own uses. Whatever uses I wanted to have, let us say I have made uses of this, till the time my uses of the resource is not complete, I will not preempt this resource. So, this is another necessary condition which is there for a deadlock to occur. Okay, the preemption of resources is not possible. So, this is the, as I said, this is third state, okay, a resource cannot be released voluntarily by the process holding it after that process has completed its task. Another characteristics for deadlock to occur is, okay, it is to have a circular wait. What does it mean by circular wait? Okay, let us say I have got this process P 1, it is waiting for P 2 to leave the resource, this is waiting for P 3 to leave the resource, this is waiting for P 4 to leave the resource, and this is waiting for P 5 to leave the resource, and this is waiting for P 1 to leave the resource. So, this is what we call as a circular wait. So, this is what we have got as circular wait. Okay, there exists a set of processes P 0, P 1, P 2 and P n, and what is happening? P 0 is waiting for a resource that is held by P 1 and P is waiting for a resource that is held by P 2, and continuing this way P n minus is waiting for a resource that is held by P n, and P n is waiting for a resource that is held by P 0. So, this is what we call as a circular wait, whereby each one of them is waiting for the other to leave the resource for its utilization. Now, how do we find out whether a deadlock has occurred or not? We go for resource allocation graphs. Basically, you might have gone through the graphs, which is nothing but a set of vertices and the set of edges. Now, what we have got is, let us say V is partitioned into two types. Let us say I have got P 1, P 2 consisting of all the processes, and R is the another set which is consisting of all the resource type of the system. Now, there are two types of edges which are there. One we say is the request edge, another is the assignment edge. What does we mean by request edge? That is, if my direction of P 1 to R j, that is R j is my resource, P 1 is the process there. If it is this direction, then we say P 1 is requesting for a resource R j, and assignment edges, okay, there is a directed edge from R j to P i, that is, okay, R j resource has been allocated to the process P i there. I think this particular thing must be very clear once you draw this sort of resource allocation graph. As I said, okay, it is nothing but a set of vertices and the edges. As I said, my vertices are of the type P and R. P is processes, R is the type of the resources, and my edges are either it is a allocation of the resource or it is the request for a resource there. So, this is how I draw it. My process I represent it as a circle thing so there, and resource type I represent it like this. Now, what does it mean? Okay, this particular resource is there and there are 4 instances of the same resource, meaning thereby okay, I have got printer, my resource type is printer, and let us say there are 4 printers. That is, let us say there are 4 printers which are available to me for the allocation purposes, and this is how my Pi request instance of the resource R j. That is, a Pi is requesting for the resource R j, or R j has been allocated to the process Pi there. This is how we show this sort of graphs. Now, this is example of one of the resource allocation graph. Let us say what is happening in this particular case is, maybe P 1 is requesting for the resource R 1, which is being held by the process P 2, and P 2 is requesting for a resource R 3, which is being held by the process P 3. And in this case, let us say this is, there are 2 instances of the resource R 2. Now, one instance of the resource R 2 is being held by P 1, and another resource of the type R 2 is being held by the process P 2 there. Now, what does this particular thing means? This is very interesting. Okay, there is I got one resource which no process is utilizing at this stage, and I have got 3 instances of the same resource there. So, this is what we call as the resource allocation graph, whereby we have got all the resources. So, this is what we have got resources, and these are some of the processes which are there, and they are being allocated some of the resources. This is through this particular edges. Now, that was just a resource allocation graph. Now, how do I find that there is some sort of a deadlock which has occurred there or not? Now, we have to find out in case there is some cycle there. What do we mean by cycle? Okay, in case I have got a node which after few transactions I reach to the same node there. I will show you in the next slide. Let us say this is resource allocation graph with a deadlock. Let us say P 1 is waiting for resource R 1, R 1 is has been allocated to P 2, and R 2, this particular resource R 2 has been allocated to P 1, and this has been allocated to P 2. And maybe this sort of a thing can lead us to some sort of a deadlock there. Okay, there is some, in this particular graph there is a cycle there which shows that this particular graph has got a deadlock. Now, as we say in case there is a cycle in a graph, we say deadlock has occurred, but this is not a sufficient condition for a deadlock to occur. Okay, this is another case where resource allocation graph with a cycle, but no deadlock. In this particular scenario, let us say this is the cycle which is there, but still this is not a deadlock state. Maybe I have got a other type of a resources which are available to me. So, this is what we say, okay, I can have a graph with a cycle, but they may not be in the deadlock state. So, these are the basic facts which are there. Okay, if graph contains no cycle, then there is no deadlock. So, this part is very clear. Okay, the moment I wanted to find out whether my processes has gone into deadlock, what I try to find out is I make a graph over there, process graph, and out of that I try to find out whether it has gone into the deadlock or not. If there is no deadlock, or if there is no cycle, I say there is no deadlock in that particular state. But if a graph contains a cycle, that is another state which is there. Now, if only one instance per resource, that is my graph has gone into a cycle, then I try to find out if there is only one instance per resource, that means there was only one printer as a resource available to me, then I say this is in the deadlock state. But if several instances per resource, then possibility of a deadlock is there. Its cycle may not guarantee a deadlock, but there is always a possibility that it has entered into the deadlock state. Now, then we have to have some methods through which we can handle this sort of a deadlocks. Okay, what we have to ensure is that the system will never enter into a deadlock state. Now, what can be the methods of handling the deadlocks? Let us say two people are fighting. That is a very interesting instance which is there. Okay, let us say there are two persons who are fighting. One of the methods is there are two other person who separates out them and the fight is over. Now, another method is I do not allow them to fight. One is that they start fighting, then I separate them out. Another is I do not allow the fight to be there. Then the third instance is let them keep on fighting till the time they complete their fights, they will lose their energies and automatically they come out of this particular fights. Same is true in case of a deadlock handling, in case of a processes also. Okay, we ensure that they never enter into a deadlock, that is somebody holds them back. The moment they try to enter into deadlock, I hold them back, or we allow the system to enter into deadlock state and then recover. That is what we do is let as I said, okay, let the moment two persons are fighting, I just separate them out. Same is the true over here, okay, let them enter into deadlock state and then they recover. Another is ignore the problem. Now, this is the situation where we are allowing them to fight till the time they consume all their energies, and we pretend that deadlock never occurs in the system. That is, let us say 5 people are watching them fighting, you just assume they are not fighting, you continue with your own work and they will stop fighting of their own. Now, this is what is being followed in most of the operating system as well as Unix. Okay, Unix what it does is it allows the processes to get into deadlock and it keeps on having them in the deadlock till the time system of its own tries to find out what are the processes which have not done anything since long and take them out. Thank you very much.